good morning, good wherever, and welcome to this webinar. As Stefan said, the idea of this is to talk about what we call compile stashing. And this is a technology that we've developed at Azure, which is intended to help get your applications start up faster when they're running on top of the JVM. Now, in order to understand what we're actually doing and how we can make this work, it's useful to have a bit of background information. So what I've done is I have created a graph. Now, this particular graph doesn't look very exciting. What it shows is what we would like in terms of the ideal performance of our application in terms of its use of the JVM itself. So from an ideal perspective, what we would like is to start our application and instantly have 100% of the maximum level of performance that we can get from the JVM. As we run our application, we continue to get nothing but 100%, and then we stop our application. Sadly, the reality is somewhat different. And if we look at a graph which is taken from more of a real world type of application, this is the thing that we tend to see. Now, it's worth spending a few minutes just to discuss what's happening in this graph and the different regions of it and how that affects our application in terms of the level of performance that it can get from both the JVM and the machine underneath. When we start our application, we use the class files that we've compiled with the Java compiler, and we run Java on those. And what happens at that point is that the Java virtual machine has to load the bytecodes. This is the most important thing because the bytecodes are in the instruction set of our virtual machine, hence the Java virtual machine. Now, a virtual machine is not the same as a physical machine. And so there's this translation between the bytecodes, the instruction set of our virtual machine, and the instruction set of the real machine, the physical hardware that the application is actually running on top of. When we start our application, how the JVM takes those bytecodes and does something with them is by what's called interpreting them. So every bytecode that it reads from the class file, it has to convert into the necessary instruction, or more likely instructions, plural, to run on the physical hardware and the operating system that we have in our machine. The fact that we have to do this, so we have to convert them from the virtual machine instruction set to the real instruction set, and we do that every time we see a bytecode, regardless of how many times we've seen it. That leads to a significant degradation in performance compared to what we would get if we had compiled this directly into native instructions. If you go right back to the beginning of Java, when it first came out, what you saw was that people complained about Java because it was slow. So it was slow compared to C and C++ applications, and it was this bytecode interpretation that was causing that loss of performance compared to the other applications. So the developers of Java looked around and they said, okay, what can we do to solve this problem? And there's already been a lot of work done on this. And what they said was, okay, let's use what's called just-in-time compilation. How this works is that you call methods to do certain operations in your application. You will get to a point where maybe you have a long running loop that calls the same method many, many times. The JVM will count how many times an individual method is called. And when that count reaches a certain threshold, the JVM will say, this is a hotspot in our code, hence the name of the Oracle JVM. What it will then do is it will say, okay, let's, rather than interpreting the bytecodes of this method every time, let's pass it to a compiler internal to the JVM and generate native instructions that we can cache and we can use every time we need to call that method. So at that point, it uses what's called the C1 JIT compiler. And in the past, this has been called the client JIT compiler. The idea of the C1 JIT compiler is that it compiles the code as quickly as possible. We want to take advantage of the performance improvement, but we need to do that very quickly. The implication of that is that it can't apply a lot of optimizations to the code that it generates. It doesn't have any profiling information to use. It just has the bytecodes to look at. And because it wants to do it quickly, it can't do a lot of analysis on the bytecode to try and figure out where it can improve performance. So it's all about compiling code as quickly as possible so we can make use of it. So we see a gradual increase in performance. At another threshold, in terms of the times that the method is called, the JVM will then decide, okay, this really is a hotspot of code. Let's recompile it, but use a different compiler. So at that point, we'll use a different JIT compiler called C2, or used to be called the server compiler. And what that will do is it will use the information that has been collected whilst the C1 code has been running, because we also collect profiling information at the same time. Compile the code, generate some profiling information. So the C2 compiler is able to spend longer compiling the code, and it's able to use this profiling information that's been collected whilst it's been running for however long it's been used. And that way it can apply a lot more optimizations to the code that's generated. What we then see is a gradual increase in performance as more and more of the methods that are needed in our application frequently get compiled. Now, as we do that, we'll see there are some dips in performance. And the dips in performance are a result of what are called de-optimizations. Once we get past that and we get all the methods compiled that we need for our application to run in a steady state, we get to our optimum level of performance. But even then, we'll see some dips in performance. And that's due to a different effect of what the JVM is doing, because the JVM handles memory management for us. Memory management includes the idea of garbage collection. So we'll see these dips where we get pauses for the garbage collector as it pauses our application threads in order to do work for collecting objects that are no longer required. So this is a very typical sort of performance graph that we get with a Java application. And what we tend to refer this to as is the warm-up time that it takes for the application. So the amount of time it takes from the very low level of performance to when we get to our optimum level of performance is how long it takes to warm up. So what I'd like to do is to ask you, the audience, a question. So if we can bring up the survey so you can answer this. Then the question is, how much of a problem is the warm-up time of your applications running on top of the JVM? And I've given you three possible answers. The first is, well, not at all. We go straight to full speed. We don't see any issue with that. Second is, it's a bit of a problem, but we have ways of managing it. And then the third answer is, we would really like to reduce or eliminate this particular part of the way that Java applications work. So if I just give you a couple of seconds more, and then if we close the poll and have a look at the results, what we should see, hopefully, is some results. Yes, there we go. Okay, so that's interesting. So 8% said it's not a problem at all. Half of the audience say it's a bit of a problem, but it's manageable, and quite a significant proportion of the audience, 42%, would like to reduce this or eliminate it completely. So that's good, because if I go back to my slides now, what I'm going to talk about for the rest of the presentation is how we can address this particular issue. Okay, now there are some common ways that people use to try and reduce the issues of warm-up time of applications. First of these is what's called application class data sharing. Now that was something which Oracle created as a commercial feature in their JDK. More recently, they've contributed it to the Open JDK source code, and it's now open source and part of JDK 11, so everybody can use it. What this does is it says, when you start your application, you have a set of classes that are required for that application. The JVM has to load those classes, it has to initialize those classes. Part of that is building internal data structures for the JVM to use of those classes. Now, every time you start the application, the JVM has to do the same work. It has to load the classes, it has to initialize the classes, it has to build the internal data structures. What application class data sharing does is say, when you've loaded those classes and you've got your application running, store all of that information, the internal data structures, as an external file. When you restart the application, the JVM, if it detects this file or is told about this file, can say, oh, okay, rather than loading those classes and initializing them, I'll simply map that file into memory and then point to that area of memory so that the data structures are in exactly the same place and it can use them without having to do all of that work. So it's a nice way of eliminating some of the overhead of class loading initialization. A second thing that people like to use in terms of trying to avoid the warm-up time is ahead of time compilation. And we're going to talk much more about this in detail later on, but it's the idea that rather than compiling into bytecodes, where bytecodes have to be interpreted and then JIT compiled, you simply say, okay, let's do all of the compilation ahead of time and generate native instructions for a given platform for that application. And then the third approach that people sometimes take is to say, well, we need our application to start working at 100% at this time. And trading applications is a good example of this. 9 o'clock is when trading starts, so you want your application to run at 100% at 9 o'clock in the morning. To avoid that problem of warm up, you say, okay, let's start our application at 10 to 9, and we'll throw some dummy transactions at it to simulate the behavior of the application and get the application to warm up so that at 9 o'clock in the morning, it's ready to go with our full transaction speed. The problem is that none of these actually address the real problems that we have in terms of what's happening inside the JVM and how to make it better. Right, so let's talk a little bit about Java then. So Java has this sort of slogan that's been around for quite a long time: write once, run anywhere. The whole idea of bytecodes enabling us to use the virtual machine, and we don't have to recompile our code if we want to run it on a Windows operating system, on an Intel platform, or if we want to run it on a Linux operating system on an ARM platform. You can take the same bytecodes and run them on exactly the same application on different machines. But this leads us to the reality of software. And in this case, what we have to deal with is two very orthogonal demands for how we write software. What do I mean by this? Well, the thing is that as people, as humans, what we like to do is to write human readable code. This is where computer languages come in. So it's a language which is similar in many respects to the way that we communicate between ourselves. What we want is something that's easy for us to understand, easy for us to see what is happening in that code, so we can see where we've got loops, we can see where we've got conditional operations, we can see where we're doing different things in our code. So that's the idea of computer languages. And computer languages are high-level abstractions of the problem that we're trying to solve. The other side of this is that the computer itself, the physical hardware, executes instructions. And instructions are simply numeric values that we pass to the CPU that represent a particular operation that we want to happen inside the CPU. Now, that could be something fairly simple, such as loading a register. It could be something more complex, like doing a vector operation on a number of distinct pieces of data, multiplication, something like that. But the reality is that we have this problem where we need to convert from the computer language, the high-level abstraction of our problem, into the low-level representation that's required by the machine itself. To do that, we use, as we all know, a compiler. So a compiler takes the language that we've written it in, generates machine instructions from that. However, the thing that we have to think about there is that the performance of the compiled code depends on a lot of different factors. There's a lot of different things that can impact on how well that level of performance we get actually is. So as I said, with the JIT compiler, we can use a quick compiler, which doesn't apply optimizations. We can use a longer compilation phase, which applies more optimizations, uses more profiling data. The reality, though, is that, as I've said here, the Highlander principle does not apply. That means there isn't a single answer. There is no one leader to rule them all. That's the Highlander principle. So we can have lots of different ways of approaching compilation, and we need to figure out what is the best way of doing that in order to get the results that we want. Now, I've already said, and I've mentioned these things, but let's talk a little bit more about the realities of ahead of time compilation versus JIT compilation. If we use ahead of time compilation, what we're saying is take the Java code that we've written and then generate from that directly native instructions. The thing that we have to do though is we have to say we're generating those native instructions for a given platform. So it could be Windows running on an Intel architecture. But even then, we have to be quite careful in terms of how we specify what particular platform we're running on, because we could potentially miss optimizations that are available if we don't specify things in a certain way. And a good example of that is that the Intel architecture has been developed over a number of years. And there are certain operations inside the Intel processor that refer to vector processing. Vector processing uses these operations called AVX, AVX2, and AVX512. The difference between these is the width of the register. So it's this idea that you can take a number of pieces of data, you can load them into a very wide register, and then apply a single instruction to the multiple pieces of data in a single clock cycle. With AVX, it's 128 bits. With AVX2, it's 256 bits. With AVX512, you'll be very surprised to know it's 512 bits. But the important thing here is that only certain processors support each of those levels of instruction. So the most modern ones will have AVX512 and AVX2 and AVX. But the older ones may only have AVX or they may have AVX2. When we compile our code, do we compile our code for an Intel architecture, in which case we have to say, well, we're making it for general Intel processors, so we can only use AVX because we know that all modern processors have AVX. Or do we compile it for a very specific set of processors where we know that they will have AVX512 and then we can get more performance from it? So that's the kind of thing where we're making decisions ahead of time about where we're going to deploy our code, and we have to be very careful about how we do that. The second thing that ahead of time compilers do is they have to do static analysis of code paths, because of course they're looking purely at the code that's been written by the developer. So all they can do is look at that code and figure out what instructions are being used, what methods being called, and so on. So there's no visibility of what is actually going to happen at runtime. They can only statically analyze things, but they don't have any ability to say what happens as the application runs. The other thing that's very important for Java applications is the fact that Java is a statically typed language, which means we can't change the type of a variable as we run the code. So that's good, but Java is dynamic in other ways. So it has dynamic class loading. When we run our application, we can load a new class at runtime, and that can replace different methods that we call as part of our operations. Things like that have a very significant impact on what we can do for optimizations. So again, optimization opportunities can be reduced by not having the ability to look at what's happening at runtime. One of the most common ways of optimizing code when you compile it is what's called method inlining. If you call a method within a loop, rather than having to push and pop a stack frame every time you call that method, you simply take the instructions of the method and you put them into the loop. That way you avoid the stack frame overhead and you still get the same effect in your code. Problem is that if you have dynamic class loading where you can replace a method at runtime, the compiler has to be very conservative in terms of which methods it can inline, because it can't guarantee that at runtime that method may not be changed by loading a new class. There's a whole range of optimizations that are called speculative optimisations, and they rely, as I'll explain in a moment, very heavily on what happens as the application is running. Because we're doing static analysis, we can't use a lot of those speculative optimizations because we don't know what's going to happen when the application runs. Now, just-in-time compilation is the opposite of that. So we compile the code as the application is running. So the downside is that we place an additional overhead on the JVM in terms of extra work that it has to do while the application is doing its work. But the important thing here is that we have lots of profiling information about what has happened with that application up to that point. We can have a complete picture of all the things the application has done up until the point where we want to start compiling. It also has a completely accurate picture of the loaded classes. So when we're talking about method inlining again, we know without any ambiguity which method is going to be called at any given time, because the JVM knows which classes are loaded and therefore which methods are going to be called. So we can use a more aggressive method inlining optimization on the code that we generate. And we have the ability to use these things called speculative optimizations, because they rely on the profiling data and knowledge of what has happened in the application to date. Let's talk about speculative optimizations. Okay, now sometimes it is better to seek forgiveness than ask permission. Now, I've heard this phrase a lot of times. When I was at Sun, this was actually sort of a mantra for actually working at Sun. But I looked this up when I was putting the slides together, and it turns out, interestingly, that this was a quote from Grace Hopper. And Grace Hopper was really the person who developed the first compiler, and that really led to the invention of COBOL. So it's kind of interesting to me to kind of use that phrase in this particular situation. But there you go. What do I mean by this? Okay, let's look at an example of where we might use a speculative optimization. I've created a simple method here, which is called compute magnitude. And compute magnitude takes an integer value, which it's going to do something with. What it then does is have an if statement, which says that if the value is greater than 9, then it has to call another method called compute bias to generate some value based on what's been passed into our compute magnitude method. If the value is not greater than 9, then we always set the bias to be 1. And then in terms of what we return from that method, we calculate the log 10 value of bias plus 99. So it's a slightly contrived example, but it's good to help you understand what we mean by a speculative optimization. If we run our application and we get to the point where we want to compile this method, and the compiler looks at the profiling data, and that profiling data shows that so far, the value that we've had passed into compute magnitude has never been greater than 9. So the bias has always been 1, and therefore we've returned the log base 10 of 100. What the compiler can then do is use that information to create a speculative optimization. Speculative optimization says the code has behaved in this way up until now. Let's assume that it will continue to behave for the rest of the time in the same way. In this case, we may have a situation where if the value exceeds 9, that's a very unlikely situation. It's like an error situation or an abnormal situation. So we can then say, okay, the compiler can recompile our code like this. It can say, okay, we know that log base 10 of 1 plus 99 is 100, so that's actually 2. Rather than calling the log base 10 method every time with the same value, let's simply return 2. But we need to make sure that if that situation occurred where the value was greater than 9, we can still deal with it, because that's a perfectly valid code path and we don't want to ignore it. So assuming that everything works in the same way, we continue to return 2 and everything works with better performance. However, if we get a value that is greater than 9, suddenly we're into a different code path, and at that point we drop into what's called an uncommon trap. Uncommon trap says, the optimization that we created was wrong. So our speculation was wrong, and we have to then throw away the code that we've compiled and go back to interpreted mode. And then we have to go through the same process where we go to C1, compile, and then we go through C2 and we recompile. So it's the idea that de-optimizations can happen as well as optimizations. And that's where we saw the dips in performance as we gradually warmed up in our graph. So one of the things that we at Azul have done is we've done a lot of analysis on code, and we found that over half of the performance benefits that we get from JIT compilation are a result of speculative optimizations. Now, that means they're very good. for performance. In fact, critical for performance. The more we can do them, the better performance we get. And ideally, what we want to do is minimize the number of de-optimizations, because that throws away compiled code. We've wasted the time of compiling it. We have to go back to interpretive mode. We have to then go back through the process of recompiling all our code again. So de-optimizations are very bad. Speculative optimizations at work are very good. Okay, how do we address the problems of warming up our application more quickly? Well, the first thing is talk a little bit about the Zing JVM, because this is where we have made changes to the OpenJDK JVM so that we can address these types of problems. So the Zing JVM is our commercial Java implementation. It's based on the OpenJDK source code, but it is fully Java SE compliant. We run all the TCK tests on it. There's about 150,000. They all pass in the way that they should. So we know that what we're producing will run Java bytecodes in exactly the same functional way as any other Java SE compliant JVM. What we then do is what we have done is modify parts of the JVM to give better performance, lower latency. So one part of that is the garbage collector. So I'm not talking about that today. We replace all of the garbage collectors in the JVM with one which is called C4. So truly pauseless collector, which basically eliminates issues of garbage collection. We've also replaced the C2 JIT compiler, the second more heavily optimized compiler, with one that we call Falcon. And I'll talk a little bit more about that as we go through. But again, I'm not really going to talk about Falcon in a great deal of detail. But it is a better performing JIT compiler than C2. And then the things that I'm really going to focus on now is ReadyNow and compile stashing, which is aimed at reducing this warm-up time for our applications. Talk about ReadyNow. ReadyNow takes the approach that what we want to do is we want to record some information about an application when it's running at full speed. So you let your application start, you go through the warm-up phase, get to the point where your application is running at the level of performance you expect, all of the methods that need to be compiled are being compiled, everything is good. You then record a ReadyNow profile, and that profile contains 4 pieces of information. The first is a list of all the classes that are loaded by the JVM at that point in time. The second is a list of all the classes that are initialized. Now, probably if you run the application for a reasonable amount of time, those 2 lists are going to be the same. But to make life simpler for us, we record them as separate lists because there may potentially be some differences. Then what we do is we record all the profiling data that has been gathered whilst the code has been running, having been compiled with the C1 JIT compiler. So the profiling information that's going to be fed into the C2 or Falcon JIT compiler is all recorded. And then the most important thing as well is that we record all the speculative optimizations that the compiler used, but which turned out to be false. So where we compiled the code, made a mistake in our assumptions, and then had to go back and de-optimize the code. Nice thing about this is that we can gather this data over any period of time that we want. It's not like we say, okay, well, you have to take this profile after 2 minutes. You can take it after 2 days, you can take it after 2 weeks if you want. And what you can also do is you can say, have multiple profiles. Assuming that your application runs in a particular environment, maybe Monday morning has a different profile in terms of the usage of that application to a Friday afternoon. You take one profile on Monday morning, take another profile on Friday afternoon. If you then really need to restart your application, you can decide, do I use the one for Monday morning or do I use the one for Friday afternoon based on the level of usage of that application at that time. So it gives you a lot of flexibility in that respect. What the information then gives the ability to happen within the JVM is to really use that information and then reduce the number of de-optimizations. And this is, as I say, something that really can help with performance, is minimizing how many of the assumptions that we make about optimizations speculatively turn out to be wrong. So if we know that those things didn't work, we can avoid them in the future. In terms of what ReadyNow does, is it says, okay, we've got this information, let's load all those classes in the list, let's initialize all those classes in the list, and then let's take all the methods that we know we need to compile and compile them using the profiling data and the speculative optimization failure data before we start the application running. So by the time you get to the main entry point where you're doing your static void main, almost all of the code will be compiled using the Falcon JIT compiler. So it'll be heavily optimized based on the profiling data, and will have avoided the speculative optimizations that won't work. Now, I say most of the code will be compiled. What we find is that the optimization level that you get when you get to your main entry point will be almost at the point that you had when you recorded the profile, but it takes a few transactions just to get it to that level that you had previously. It really is only a few. It's somewhere between 1 and 5 transactions will normally generate the level of performance that you want. Things like lambda expressions can be a little bit challenging. We're still working on some of the details of improving that, because lambda expressions use the invoked dynamic bytecode so that they can shift the responsibility of the implementation of a lambda expression from compile time to runtime. And there's a few issues that we have in terms of how to optimize that. But again, it's something we're working on. But ultimately, the results of this are very good. So if we look at a graph again, this is a simplified version of the graph that I showed you earlier, where we've got the warm-up time. So we start off and we have a sort of slope where the performance gradually increases until we get to our steady state. That's without ReadyNow. If we look at it with ReadyNow, we get a better graph. So now suddenly we've got a much steeper graph where we're compiling all the code, we're getting everything running, and so we can get to our maximum level of performance very, very quickly. And we have overall much better performance. But obviously there's a little bit of a drawback to this, because the work that the JVM has to do in advance of getting to your main entry point means that there's a certain amount of time when your application just isn't doing anything as the JVM gets it ready to do its work. So this is where we do our class loading, it's where we do our initializing, and we do our compilation of our methods. So what we really want to do is we want to minimize that particular feature as much as possible. Now, this is a slightly different approach in terms of the graph. This is looking at the transaction latency and how ReadyNow can affect the performance of our application. This uses 2 different profiles that were generated. The original, without using ReadyNow graph, shows that we start off with very high latency. We then go through a sort of gradual improvement where we've got spikes as we de-optimize, and then it sort of settles down. With the first generation profile, we get a better initial performance, and we've got an interesting sort of anomaly, I should say, more towards the right-hand side of the graph, where we see a bit of a uptick in latency associated with that profile. But with the second generation profile, we bring that down even further, and we get a nice flat line in terms of our performance. So this just gives a sort of picture of how ReadyNow can really reduce the latency of initial transactions for our application. Let's talk a little bit more and review what we said about how Java and the JVM works. So we start off with our source code file, our human readable form of .java. We run that through Java-C, and we create a class file. Class file contains bytecodes. Bytecodes are instructions in the JVM instruction set. In order to run that application, we call the Java executable Java. We pass the classes, the class path, that type of information, and that executes the JVM. Within the JVM, that has to do some work in terms of loading the classes, and it does some dynamic verification, it does some dynamic linking so that it can establish which methods need to be called and where they come from and various things like that. In terms of generating instructions to be executed by the physical machine, as I said, we use the interpreter. So the interpreter will convert from bytecodes into machine code, run on the physical machine. As we warm up, we profile, we count how many times a method is used, and then when we reach the threshold, we go to C1. Profile data, compile as quickly as possible, and then we pass that on to Falcon to optimize and generate the most heavily optimized output in terms of machine code. So that's the process that we're going through. If we look in a little bit more detail at Falcon, and we've got ID optimizations as well, I should say. If we look at the Falcon in a little bit more detail, inside Falcon, we've used a thing called the LLVM project. And LLVM is a compiler project that's designed initially for static-based compilation, AOT compilation, and lots of people contributing to that. There's people like Sony, there's people like Microsoft, AMD, NVIDIA, Intel, ARM, all contributing code to this. There's lots of people who understand about compilers. How this works in terms of the JIT compilation is that we take the bytecodes of the method that we want to compile, and we convert that along with profiling information into what's called an intermediate representation. And LLVM has its own intermediate representation that we convert to, and we pass it to the compiler and we say, compile this method. LLVM will look at that method and it will do some analysis on it. And what it needs to do as well is to query the virtual machine about certain things. So it will send queries to the virtual machine in order to establish certain facts about that method so that it can figure out the best way of compiling it. Good example of that is, again, coming back to method inlining, where the compiler says, well, I think we should be able to inline this method, but I really need to make sure. So we'll send a query to the virtual machine through a callback method and say, can this method be devirtualized? And if it can be devirtualized, then we can inline it. If the response comes back as yes, that can be devirtualized, then the compile code will inline that in the loop and get better optimization. If it comes back and says no, then it has to leave it as a method call. Having done a number of queries and responses, it then generates a compiled method, and it will generate machine code based on all the information it has, as optimized as possible. So this is the way this works. Now, the principle behind this is entirely deterministic. What do I mean by that? Well, if we look at a single method that we want to compile, we can put together a sort of box of information there. And we can say that for that method, we can have the initial intermediate representation, what we're going to send to the LLVM compiler. That's the method bytecodes and the profiling information. We also have some information about the queries that are sent from the LLVM compiler to the virtual machine through callbacks and the responses that we get to that. And then finally, we have the machine code that is produced from that set of information. The deterministic nature of this says that if we have identical input in the form of the initial IR and the queries and responses, then we can guarantee that the machine code that we generate is going to be identical. This fact is very useful to us in terms of how we can optimize the way that our startup process works. Because what we can do is we can say, right, when we record the profile for ReadyNow, what we'll also do is we will store all of the compiled methods that we have. So all of the machine instructions for those methods we can dump to a file, and we call that our compile stash. Now, rather than having to go through this process when we start up the application, where we take the methods we know we have to compile, pass the intermediate representation to LLVM, have it do the queries and responses, go back, generate machine code, what we can actually do is replace that with the compile stash. And the compile stash, we can pass in the LLVM intermediate representation along with the information about the queries and responses. So we have this definitive definition. We have a definition of the method completely, and we can look in the compile stash and we say, is this code that was generated for this method based on this profiling information, based on this intermediate representation, the same as what we're trying to do now? If it is, we simply return the compiled code from the compile stash. We don't have to go to LLVM, we don't have to recompile it. If it isn't, obviously we then pass the information onto the LLVM compiler, it goes through the same process. Now, in terms of controlling this, we can set the size of the stash that we want for our code. By default, it is a pretty hefty 10 gigabytes. You can make it smaller if you want, you can make it bigger if you want, and you can also get statistics printed out about the way that the compile stashing is working. You can see how many compiles were performed, you can see how much compile time was involved, how many matches you got, how many misses you got, all the sorts of things that will sort of show you how well compile stashing is working for your application. So if we go back to the graph that we had before, if we look at using ReadyNow, we have this idea of, okay, so we've got much better, much steeper improvement in performance, but we have this time that it takes before the application can actually start running. That's without compile stashing. If we employ compile stashing, then we can actually shift that whole graph to the left and reduce the amount of time quite significantly as to how long it takes to actually get the necessary code compiled and everything running. What we found in terms of the analysis we've done is we can get up to an 80% reduction in compile time and up to 60% reduction in a CPU load time. So that really does, shrink down the effect of using ReadyNow and the overhead of having to do the advanced compilation. So by combining these two things, we get a really nice way of massively reducing the effects of warm-up on a Java application. Just to summarize, so essentially, as I say, we've kind of talked about two things primarily here. ReadyNow, which is recording a profile of how your application runs at a particular point in time. Then we know which classes to load, we know which classes to initialize, we know which method to compile. We can use the profiling data that we gather to aid the optimization of the Falcon JIT compiler. And we know which speculative optimizations to avoid so that we don't have to waste time on that. Compile stashing sort of takes it to the next level. So we cache the compiled code from the particular run of the application. Then if we get a match between both the method and the profile, we can avoid having to recompile it at startup time. You can simply reuse the cached version. And that really does reduce the time required to enable our application to start. If you're interested in this, you can try Zing free for 30 days. There's a web address here, so you go azure.com, Zing trial download, and you can download it from there and try it on your application and see just what a fantastic level of performance it will give for you. So with that, that is the end of the presentation. What I'll do now is I'll have a look and see whether we have any questions. So if anybody has any questions, please feel free to type those into the question box. So I've got one question here, which is, why can we not simply use the saved compiled code when we restart the application? Yeah, this is a sort of, it's kind of like, if you think about the idea of, okay, so you do a ahead of time compilation, that generates a set of instructions which you can use to start your application. Why shouldn't you just be able to run the JIT compiler, have heavily optimized code, and then restart your application with exactly the same code at the beginning? Well, there's a couple of reasons you can't do that. The first of those is that the JVM specification says that you have to do certain things as you start the JVM, and you can't just simply reload code. But there's also things that would invalidate the code that had been compiled directly in certain situations, so you need to be careful about that. Right, so a question here, what version of Zing includes stashing? Yeah, it is actually the most recent one. So I think it's the, whatever the one that was released in January, I think is the one where compile stashing is available by default. But certainly the one that you can download from the website at the moment has compile stashing in it. Another question, I'm assuming the compile stash needs to be rebuilt on new code deployments. Oh yes, very much so. In fact, even ReadyNow, if you change the code that you use, so if you recompile code, then that basically invalidates any of the saved data because of simply, we can't take into account the fact that if you've changed your code, any compiled stash code is going to be wrong. And in fact, even the ReadyNow profile might work, but it's much better to create a new one. Another question, how does this work with slightly changed apps, e.g. in development environments? Again, if you change the code, then that invalidates any stashed compiles because the compile is based on a given set of instructions. And in order to be deterministic, we have to have the same inputs. And the same inputs is going to be not just the profiling information, it's also going to be the bytecodes that generated from that actual method. So theoretically, if you changed a method, but the bytecodes that were generated by the Java C compiler were not different, which probably means that there's no real difference, well, there were no real difference, then you could use it. But ultimately, any changes to the bytecodes are going to invalidate both ReadyNow and compile stashing. Okay, so I don't see any more questions. I'll give people just a few more seconds to see if anyone has any other questions. Otherwise, I hope that this has been useful to you and interesting. Because I don't see any more questions, I will say that that is the end of the webinar, and thank you very much.